So thank you again.
Okay, bye.
Yeah, and apologies for the delay to everyone else. So okay, so our next speaker is Woojin Kim, who will be talking about the persistent topology of dynamic data. Yeah, thanks Woojin for accepting the invitation, and then you can start now if you want.
Thank you for introduction. Can you hear me?
Yes, yes.
Okay, thank you for the introduction, and thank you organizer, specifically Boumediene, for giving me this nice opportunity to talk about my research. Yes, hello everyone. My name is Woojin Kim from Duke, a first year postdoc at Math Department. Today, I'm going to talk about main ideas of persistent homology and how to use persistent homology for studying dynamic metric data. This talk is based on joint work with Facundo Memoli at Ohio State, who is my PhD advisor. And this work is supported by the following NSF grant. So let me start with ideas of persistent homology, and we are going to move on to how to use persistent homology for studying dynamic data. So the persistent homology. So data in practice is given in the form of a point cloud, or more generally, finite metric space. For example, we can sample finite number of points from a manifold, and we might want to infer the shape of the underlying manifold by looking at the finite sample. And another example would be, we can imagine a large spreadsheet, which includes many different rows, and each row corresponds to a person's biometric data. And imagine that we plot this entire spreadsheet in the Euclidean space, then we are going to have some point cloud. And of course, the shape of the point cloud will give us some insight about the data set. Then the question is, how can you quantify the topological features of this sort of data set? One idea could be putting some higher dimensional structures on top of the point cloud so that we can see the shape of the data set more explicitly. So suppose that we have a metric space. That means that for every pair of points, we have a distance between them. There might be some dissimilarity measure between two data points. Then we can define delta-Rips complex as follows. So delta is a positive number. Then the delta-Rips complex of the metric space is the abstract simplistic complex, which consists of all subsets A of X, where for every pair of points in A, the distance between them is less than or equal to delta. For instance, if I choose a certain delta for this metric space, that delta-Rips complex may look like this. So there is an edge between 2 points because the distance between them is less than or equal to delta. And there is a triangle on top of 3 points because the pairwise distances are less than or equal to delta. Okay, there are many good theorems about delta-Rips complexes. For example, if we combine a theorem by Hausmann and Leschep, then we can say that if we sample finite number of points from a closed Riemannian manifold, say that finite sample is dense enough, then for a good choice of scale delta, the geometric realization of the delta-Rips complex is homotopy equivalent to the underlying manifold. And also there are tons of applications using delta-Rips complexes in the literature. So all these are very nice, but note that in general, we do not have any access to the underlying manifold of the sample, even if there is any. So in general, we do not have any good rationale for choosing certain delta and say that, oh, this is the structure of the data set. We don't have any good choice for such delta. So here, the main philosophy of persistent homology comes in. Instead of picking a certain delta, why don't we track the evolution of delta-Rips complexes as delta grows from 0? If we do that, given such input metric space, we are going to have the following increasing family of simplistic complexes over real line. So in these small scales, we have only few edges. But as delta grows, we are going to have more and more edges in the simplistic complexes. And triangles will come in, and tetrahedra will come in, and more higher dimensional simplices will be placed on top of the data set. Then one thing to note from this filtration is the functoriality. Not only are we sending each delta to the delta-Rips complex, but also whenever we fix two different values, delta and delta prime, there exists an inclusion map between the corresponding simplicial complexes. This is called functoriality, and it plays an important role in topological data analysis. So by applying the homology functor to this filtration, we obtain the so-called Rips persistent homology of the metric space. So if the functor was taken in the coefficient field, some field coefficients, then we can represent this persistent homology as the so-called barcode or persistent diagram, which is a fundamental theorem in topological data analysis. So these barcodes encode multi-scale topological features of the given data set. More specifically, the zeros barcode encodes multi-scale clustering features of the data set, and the first barcode encodes loop-like structures in the data set, and the second barcode encodes void-like structures in the data set. So let's take a closer look at the zeros barcode. At this small scale, there are many different connected components in the simplicial complex, and that number of connected components actually correspond to the number of intervals, including this scale in the zeros barcode. But as delta grows, more and more edges will come in, and therefore connected components will merge. Those merging events are encoded by the end of intervals, even if I'm not explaining which interval should continue and which interval should discontinue. Beyond this scale, we only see just one connected component. That's why we have only one interval keeps going. And if we look at the first barcode, let's observe that at this small scale, we do not have any loop in the simplicial complex. But getting to this scale, we start seeing two loops in the simplicial complex. Those two loops correspond to these two intervals in the first barcode. Now getting to that scale, we have one additional loop. So that new loop corresponds to the interval which is born just before this scale. And getting to that scale, this the last loop was filled up by two triangles. That's why these intervals do not exceed this value. But still at this scale, we have three loops, and those three loops correspond to three intervals in this H1 barcode. So in this way, the first barcode encodes the birth and death of cycles, the one-dimensional cycles in the simplicial complexes. And in the second barcode, there is only short bar. That's because here we can see like some void enclosed by several triangles, but that is soon filled up by tetrahedra. That's why we have this short bar. So in this way, the barcode encodes multi-scale topological features of the simplicial complexes, the filtered simplicial complex. And in general, the long intervals in the barcodes are considered significant topological features of the data set, whereas short intervals are usually considered less significant, or maybe they are there because some noise points in the data set. This is not always the case, like correct interpretation, but that's often the case how to interpret these barcodes. Okay, so again, let me emphasize that this barcode representation theorem was possible because we had functoriality. For different choice of delta and delta prime, we had the relationship between the simplicial complexes placed at delta and delta prime. Okay, so another fundamental theorem about persistent homology is the stability theorem. So let me explain. There is a notion of Gromov-Hausdorff distance between metric spaces, which measures how far two metric spaces are from being isomorphic. And there is a notion of interleaving distance between persistent homologies, equivalently the bottleneck distance. Then this theorem says that 2 times of the Gromov-Hausdorff distance is an upper bound for the interleaving distance between the corresponding persistent homologies. Then one implication is that this persistent homology, sending each metric space to each barcode, is a stable process. It's stable summarizing process. And another remark is that computing this left-hand side is often much easier than computing this right-hand side distance. So therefore, when you would like to classify shapes which are modeled as metric spaces, it's often more useful to make use of this left-hand side distance rather than using the right-hand side distance. As a matter of fact, computing the Gromov-Hausdorff distance is NP-hard problem. Okay, now we are ready to move on to the Pearson homology for dynamic data. So the motivation is topological study of collective behaviors. So as you already know, there are many instances of collective behaviors in nature. A flock of birds or a school of fish or swarm of bees. So given such collective behaviors, we can observe that the distances between entities change over time. Therefore, we can see them as dynamic metric spaces. So before going further, let me show you very interesting videos about short videos about collective behaviors, which I always show whenever I introduce my research, because that motivates a lot my study. So let me use my iPad to show that video. Okay.
The universe tends toward chaos. But sometimes patterns emerge, like a flock of birds in flight. But how? How does a group of animals, or cells for that matter, work together in an organized way when no one's in charge? Like termites building skyscrapers out of mud, or fish schooling to avoid predators. It's called emergent behavior, order emerging from chaos. And you don't just see it in nature. Enter the kilobot, a robot the size of a quarter developed by engineers at Harvard. What's so interesting about kilobots is that individually, they're pretty dumb. They're designed to be simple. A single kilobot can do maybe 3 things: respond to light, measure a distance, sense the presence of other robots. But these are swarm robots. They work together. The kilobots can organize themselves into shapes, sort of like how cells form into an organ in your body. Here's how it works. The kilobots are programmed.
Okay, let me stop because we don't have too much time. Okay, let me go back to my slides. Right, so that's very fascinating video. I really like that video. So as we saw from the videos, you can see like a lot of dynamic geometry going on from the collective behaviors. So therefore, it's natural to use precision homology to measure, to quantify topological features of dynamic metric data as well, collective behaviors. So really, the researchers recently started using precision homology for studying dynamic metric data. For example, Dr. Munch's PhD thesis considered time series of precision homology derived from dynamic point clouds. In a certain section, she discussed some stability results about time-varying precision diagram derived from dynamic point clouds. And also Topology and Myra Halverson used also time series of precision homology to capture some features of swarming behaviors which haven't been captured by some classical analytic method. In a sequel work by Topology and Myra and Ulmer, they used time series of precision homology again to test the validity of mathematical model for collective behaviors. So the goal of my talk is to build a precision homology framework specialized for dynamic metric spaces, which will be a little bit different from considering time series of precision homology. So remember that flocking of birds or any collective behaviors can be seen as a dynamic metric space. Then the questions are the following. How can it quantify the behavioral difference between dynamic metric spaces so that we can systematically classify collective behaviors? And how can it summarize topological features of a dynamic metric space given that such topological features are time evolving? So remember that these sort of questions have been already well addressed in the setting of static metric spaces. So remember we had the Gromov-Hausdorff distance to measure the difference between metric spaces. And we are able to summarize metric spaces into barcodes to encode multi-scale topological features of metric spaces. And we also had the notion of distance between persistent homology. And this process was stable. So my goal is to extend actually this hoop framework to a dynamic setting. So specifically, I would like to have generalization of this stability theorem. So what I'm going to talk about from now is really about this main theorem. So I'm going to define precisely the definition of dynamic metric space, which is a mathematical model for collective behaviors. And then we are going to define the spatial temporal Persistent homology over dynamic metric space, which is going to be multiparameter Persistent homology derived from a dynamic metric space. And then we are going to discuss a certain notion of distance between dynamic metric spaces, which measure behavior difference between dynamic metric spaces. And that is going to be a generalization of the Gromov-Hausdorff distance. And there is a notion of interleaving distance between multiparameter Persistent homology, which is very well known in topological data analysis community. And this theorem then says that summarizing a dynamic metric space into spatial temporal Persistent homology is stable summarizing process. Okay, let's start from the definition of a dynamic metric space. So a dynamic metric space is a pair of a set and time-dependent function on that set. For simplicity, let's assume that X is a finite set and we have a time-dependent distance function on X. There is a function from R cross X to non-negative real. And this red R stands for time. So whenever we fix a certain time, we have a metric on the underlying set X. And for every pair of points in the underlying set, the distance between them changes continuously as a function of time. Also, for every different point in the underlying set, the distance function as a function of time is not identically zero. If that's identically zero, then we can just throw away one of the points so that we don't have any redundant point in the underlying set. Okay, that's the definition of a dynamic metric space. Now, one remark is that each point in the underlying set keeps its one identity over time. We are not just looking at a time series of different pictures of metric spaces. We are keeping really identity over each point over time. That's implicit in this definition. And examples, we can imagine some labeled dynamic point clouds, which are moving continuously in the Euclidean space. And another trivial example is going to be constant dynamic metric spaces. Dynamic metric spaces which don't move at all. Okay, we defined the notion of dynamic metric space. Now we are going to define the spatial temporal Persistent homology over dynamic metric space. Remember that now we have not only just scale, but also time as a variable. Then maybe one of the natural parameter space is going to be time cross scale space as a parameter space. Okay, but let's consider the following scenario. We fix two different times T1, T2, and two different scales, delta and delta prime. And let's consider delta Rips complex at time T1 and delta prime Rips complex at time T2, derived from this dynamic metric space. Then we usually don't have this inclusion relationship. The delta Rips complex at time T2 is not contained in delta prime Rips complex at time T2. That's not necessarily true. But what we have from this picture is that whenever we fix a certain time in a vertical direction, in the scale direction, we have a growing family of simplicial complexes. So we have a functoriality in the vertical direction, but we don't have functoriality in the horizontal direction. So that's in a way unsatisfactory. This parameter space is not enough to define multiparameter Persistent homology. So we are going to change our perspective a little bit. Instead of considering timeline, we are going to consider the collection of time intervals. So by int, we are going to denote the collection of all closed finite time intervals. By the way, I'm keeping using this red text for denoting time relevant parameters. So then this collection of all closed time intervals can be expressed as the upper half plane above the diagonal line. So the point t1, t2 will correspond to the closed time interval t1, t2. Then whenever we have two time intervals where one contains the other, the point corresponding to larger interval is located at the upper left part of the point corresponding to smaller interval. You can see that from this picture. Okay, let's keep this in mind. We can represent this int collection as the collection of points above the diagonal line. We are going to put this picture in the three-dimensional space. Specifically on the xy plane, let's put here. And then let's fix a certain interval I, which is a point in this region. And at the height delta, we would like to assign a certain delta-Rips complex. That delta-Rips complex is going to be defined as follows. There is a delta-Rips complex over the underlying set x, where the distance function is the minimum distance over the time interval I. That means that there is a collection of all subsets A of x, where for every pair of points, there is a moment in the time interval I such that the distance between those 2 points is less than or equal to delta. So for instance, if we look at this picture, there is an edge between these 2 points because there was a moment in the time interval I such that the distance between these two entities was less than or equal to delta. And there is a triangle because pairwisely there was a moment in the time interval I such that the distance between pair was less than or equal to delta. The elemental pair is less than or equal to delta. Okay, now let's fix another time interval I prime, which contains I, and another delta prime, which is greater than delta. Then the delta prime Rips complex cross over the time interval I prime is actually larger than the delta Rips complex over the time interval I. So why is that? Because the distance function here on the right-hand side is smaller than the distance function on the left-hand side. And furthermore, we fixed larger scale value, delta prime, than delta. Therefore, in the picture, if we look at our parameter space, as my point moves left back upward direction, the corresponding complexes get bigger, right? So that means that we have three-dimensional simplicial filtration. Now, by applying the homology functor to this entire filtration, we obtain the so-called spatial-temporal Pearson homology over dynamic metric space. So if I choose field coefficient homology, then we are gonna having functor from this poset to the category of vector spaces over a certain field. So one remark is that if the given dynamic metric space is constant at a certain static metric space x dx, then this spatial temporal Pearson homology is actually constant with respect to the factor int, right? Because gamma x do not change over time, so whatever my interval is, my simplicial complex will not change depending on the choice of I. Therefore, we can neglect this first factor and regard this three-dimensional filtration as a vertical one-dimensional filtration, which is the same as just a standard Pearson homology of a static metric space. And also, when we have two dynamic metric spaces which are constant respectively, x dx, y dy, then the interleaving distance between spatial temporal Pearson homology is actually the same as the interleaving distance between the corresponding Rips Pearson homology of corresponding static metric spaces. Okay, so we defined spatial temporal Pearson homology for a dynamic metric space. Now I would like to explain which features of a dynamic metric space are considered significant. So which features of a dynamic metric space correspond to topological features of a metric space, which result in long bar in the barcode. So one unfortunate thing is that we do not have a notion of barcode or Pearson diagram for multiparameter Pearson homology. So that's unfortunate, but still, I'd like to claim that large homological features in a dynamic metric space, which persist for a long time, are considered significant feature in our framework. Here is the reasoning for that claim. So suppose that we have a dynamic metric space gamma x, and we are going to consider this value, which is the interleaving distance between first Pearson homology of a single point space and first Pearson homology of gamma x. Then of course, single point space has no loop structure. Therefore, first homology is trivial, like everywhere zero space in my associated to my point in the indexing space. Whereas this first homology might have some one-dimensional feature. Therefore, the value in this yellow box can be regarded as some sort of norm of the first homology of gamma x. And it is not difficult to check that this value can be large only when gamma x contains large circular configuration which persists for a long time. That's why I said that these large homological features which persist for a long time are considered significant. And the same principle holds for other orders of homology. For example, let's consider the zeroth homology, corresponding zeroth homology here. Then the corresponding value for this yellow box can be large only when this gamma x contains two subclusters which are for each other, which are far from each other, and these subclusters configuration persist for a long time. If that happens, then this yellow value corresponding to zeroth homology is going to be large, and other order of homology as well. Okay, so now let's move on to the definition of distance between dynamic metric spaces. One very natural metric we can imagine is actually the integration of the Gromov-Hausdorff distance across the timeline. However, that metric is not always discriminate enough. We are going to see that from this example. So let's imagine two dynamic metric spaces. Both of them consist of 3 points. And here is the first one. 3 points are on the real line. The 2 points are fixed at -1 and 1. And the middle point has time-dependent coordinate sine of t. Therefore, this middle point oscillates between the other 2 points over time. And the other dynamic metric space is almost same, but the middle one has a little bit different description. It has absolute value of sine of t. Then this middle point will oscillate between the origin and the right-hand side point. Then one thing we can observe is that whenever we fix a certain time, two fixed metric spaces are isometric. Sometimes they have exactly the same picture. Sometimes one is obtained by reflecting the other with respect to the origin. Therefore, if we integrate the Gromov-Hausdorff distance against the time interval, you're going to have 0. Also, if you remember the standard stability theorem about Pearson homology, the interleaving distance between the corresponding Pearson homologies is going to be 0 for every time. Therefore, integrating this function is going to be also 0. That means that using these integrations as a metric will not discriminate these two dynamic metric spaces. However, if you view these dynamic metric spaces as collective behaviors, they are clearly different, right? Therefore, I would like to have some metric that can discriminate these two dynamic metric spaces. So before introducing our metric, let me introduce a notion of strong isomorphism between dynamic metric spaces. So two dynamic metric spaces are called strongly isomorphic if there exists a bijection from one underlying set to the other underlying set, such that for every time, this bijection serves as an isometry between the fixed metric spaces. So here is a known example. So whatever the bijection is, you choose from one underlying set to the other underlying set. Both of them consist of 3 points. You can see that that does not serve as an isometry for all the time. It can serve as an isometry for certain times, but it fails to be an isometry for all the time. Therefore, these two dynametric spaces are time-wisely isomorphic or weakly isomorphic. And our motivation is to define another metric which can discriminate weakly isomorphic dynametric spaces. Specifically, we should discriminate these two dynametric spaces. Okay, here is the definition we have. The distance between dynametric spaces is defined as the infimum of epsilon for which gamma x and gamma y are epsilon interleaved. Okay, what do I mean by two dynametric spaces are epsilon interleaved? That means the following. So there exists a correspondence between the underlying sets x and y. Correspondence is nothing but a relation such that for every point x in x, there exists a point in y such that x comma y belongs to R. And conversely, for every point y in y, there exists a point x in x such that x comma y belongs to R. That's called correspondence. And it must satisfy the following property. For all time, for every pairs xy, x prime, y prime in R, the distance between y and y prime at time t should be an upper bound for the minimum distance between the corresponding points x and x prime over the time interval from t minus epsilon to t plus epsilon up to 2 epsilon slack. So in the picture, let me explain again. I pick any 2 points from one dynamic metric space, and I look at the corresponding elements in gamma y, and I measure the distance between these two entities at time t. That should be an upper bound for the minimum distance between these two entities over time interval from t minus epsilon to t plus epsilon up to 2 epsilon slack. And the symmetric condition must also hold, like change the rows of x and y's. Then we say that gamma x and gamma y are interleaved. I got some questions, so shall I see the answer? Okay, I see. I think I already answered, right? Am I right, Andy?
Yeah, you can unmute if you want, Andy. Yeah, Art, I think she can carry on because he's
Sorry?
Yeah, I think just carry on because he's not unmuted.
Okay. Yeah. Okay, so yeah, one thing to note is that whenever we have epsilon prime, if gamma x and gamma y are epsilon interleaved, then gamma x and gamma y are also epsilon prime interleaved for bigger epsilon prime. Therefore, defining the metric, the distance between gamma x and gamma y as an infimum of epsilon for which gamma x and gamma y are epsilon interleaved makes sense. And another remark is that whenever gamma x and gamma y are constant dynamic metric spaces at x dx and y dy, then this distance on the left-hand side is actually equal to the Gromov-Hausdorff of distance between the corresponding static metric spaces. If you are familiar with the Gromov-Hausdorff of distance, checking this equality is not difficult. So remember that this was the condition we had for having gamma x and gamma y are epsilon interleaved. Now, if gamma x and gamma y are constant, like static metric spaces, then we can neglect all these time-relevant terms. Then we can reduce this condition to this simpler condition without any time parameters. And this condition is actually what exactly we need to claim that static metric spaces has Gromov-Hausdorff of distance less than or equal to delta. Okay. And let's consider the collection of all bounded dynamic metric spaces. A certain dynamic metric space is called bounded if there exists constant such that the distance between any two entities never exceed the constant. Then the function we defined in the previous slide is really a metric on the collection of bounded dynametric spaces up to strong isomorphism. So specifically, we can discriminate these two time-wisely isomorphic dynametric spaces because they are not strong isomorphic. Okay, so far I have explained this stability theorem, all the elements in this stability theorem, except the interleaving distance between multiparameter homology, but that's not center in my talk. One thing to remark is that once again, whenever we restrict ourselves to constant dynametric spaces, this entire inequality reduces to this inequality in the standard stability theorem. Okay, now let's consider computational aspects of our framework. Remember that we wanted to have some metric which can be used for classifying collective behaviors. But one unfortunate news about this stability theorem is that the distances on the right-hand side and the left-hand side, both of them, computing both of them are very difficult. Both of them NP-hard problem to compute. So remember that the right-hand side was a generalization of Gromov-Hausdorff, but Gromov-Hausdorff is already known to be NP-hard to compute by Schmidl, and the interleaving distance between multiparameter precision homology is also known to be NP-hard to compute, proved by Bizerke, Botnan, and Kerber. So what we do in our paper is to find another lower bound for this left-hand side. So we consider some invariants of special temporal precision homologies, which are called dimension function and rank functions, and we adapt the Patel's illusion distance to measure the distance between these two invariants. Then using that distance, that lower bound can be computed in polynomial time and still good enough to discriminate these two dynamic metric spaces. So we are happy with that lower bound. So what we did is actually using that lower bound, we classified simulated flocking behaviors, which I will introduce now. So this experiment was carried out with the help together with Nate Close and Jane Smith. Both of them are graduate students at Ohio State and University of Minnesota. To generate the dynamic metric spaces, we used a variation of Boyd simulation. So let me show you Boyd simulation and explain how we carried out our experiments. So for that, let me again stop sharing and show my iPad. Share content. So the Boyd simulations look like this. So on the right-hand side, above, you can see some panel. That panel includes many different parameters we can tune. So if I increase like cohesion parameter, then the entities try to be cohesive to each other. They come together. And if I increase the alignment parameter, they try to be aligned with their neighbors. And if I increase separation parameter, then they try to be separate to each other. So by tuning these parameters, we can generate many different dynamic metric spaces. So by tuning these parameters, we identified 4 distinct behaviors which look like these. They really look different. So for each parameter setting, actually there is another behavior 5, but unfortunately that is not contained in this video. But anyhow, we identified 5 different behaviors. For each parameter setting, we run the simulation 100 times so that we have 500 dynamic metric spaces. And we tried to classify those 500 dynamic metric spaces using the lower bound I introduced. So let me show you the result of that classification task. Again, so we have 5 different distinct behaviors and repeated simulation 100 times for each behavior with random initial configurations. So they are all different dynamic metric spaces. We constructed 500 by 500 illusion distance matrix, which measures the difference between zeroth order spatial temporal Pearson homology of dynamic metric spaces. We carried out hierarchical clustering and MDS plotting. Oh, sorry. Okay, so this is the result of hierarchical clustering. 5 different colors correspond to 5 different parameter settings. So they are very well clustered, actually. Even if you can see some mix of behaviors here, this part, but overall, the classification result is quite good. And this is the result of multidimensional scaling. The 5 behaviors correspond to 5 different colors. Quite good. So here's a summary. We defined spatial temporal Rips filtration for dynamic metric spaces, which was stable with respect to the metric we introduced on dynamic metric spaces. And on the collection of constant dynamic metric spaces, our stability theorem reduces to the standard stability theorem about metric spaces and Rips persistent homology. Also, I showed you classification task using Woojin simulation. You can find theoretical details from this paper, and you can find these computational experiments and quote from this website. And you can find videos and images. Many images in my slides are actually coming from Robert Grist's paper, nice paper. And you can find the video I showed you from this YouTube video. Thank you for paying attention.
All right, thank you very much. Any questions? Yes, yeah, Robert.
Yeah, wonderful talk. That was very beautiful and very interesting. Thank you.
Thank
I
you.
have a couple of questions.
Yes.
The one is with your multi-dimensional persistent homology, and you say there's no barcode or persistence diagram. So is the problem that maybe you can't choose a consistent basis for kth homology?
Yeah, right. Like it's difficult, right? Finding consistent basis for.
Yeah, so it might be that some examples there is a consistent choice of basis, but I agree, not in general.
Right.
And then the other question is, what if there are births or deaths?
What are the births and deaths in the context?
Yeah, so you add new points to the metric space at some time, or you delete some, or you merge them, or you branch. Can you handle that? It looks like a natural extension might be possible of what you've done.
I see. So you mean like some points can appear in the middle of dynamic metric space and disappear?
Yeah.
Okay, that 30% does. Yes, I think actually I got this question quite many times from audience. Maybe that's from like practical perspective. That's the many cases in real data. So I think, yes, I think we can extend our framework to that definition of dynamic metric space, which allow births and deaths of entities. We should be careful about stability theorem and how to define metrics between such blinking dynamic metric spaces. But defining this multiparameter Pearson homology for such metric spaces will be not difficult. I think it will be straightforward. That's my thought. Yeah.
Good. Thanks.
Yeah. Thank you.
Yeah, I have a question.
Yes.
This flocking or collective behavior is known to be leaderless.
What do you mean by leaderless?
No leader.
Oh, yeah, I see.
Right. Now, you mentioned circular, and my question is, why in all these problems, even if we take some casual time series of dynamical system, we end up with those circular behavior or periodic or quasi-periodic behavior.
Okay.
What is the nature of that periodicity in different forms and the connection to being leaderless. So it's physics, I'm asking physics and mathematics in the same time.
Okay, I can see vaguely your points, but I'm not fully understanding your questions. Right, so, okay.
Okay,
so,
let's start with the circularity or the periodicity. Why when I do persistent homology or any persistence, I end up with circular?
So that periodicity, so that circular means is about time, right? The behavior is periodic. It's not about the shape of collective behaviors is circular, right? So you're talking about the periodicity of a behavior, not the shape of the behavior. Am I correct?
Yeah, you are correct, but let's go again to the leaderless. If there was a leader, he would leave the circle and go straight. If there was no circularity or periodicity, we will not have attractor to the collective behavior. Okay, we will not have this circularity or repetition. They will go to infinity and disperse.
Okay.
So there is some intuition here, but the beautiful mathematics that you showed up, going with Gromov and Hausdorff, has to do with some underlying attractor.
I see.
And apparently the whole population has biologically now, or neuroscience, some sense of that attractor, but of course without mathematics, but in their senses. The sensory system is kind of feeling that there is some underlying attractor controlling their motion or collective behavior.
I see. Okay, right. That's a good point. Yes, I wanted to also find like connection between our ideas of this Gromov-Hausdorff framework and more physical, like a point of view, like having leaders and some attractors. That kind of
it's
factor
very intriguing questions here.
Right.
And also in neuroscience, and Duke people can tell you a lot about it, there is a lot of periodicity. The whole time series, it's actually analysis of periods. The spiking and non-spiking, the inhibitory, and anyway, you know what I'm talking about.
Yeah, I think so.
Okay.
Thank you for feedback.
All right, thank you. Any other questions? Yeah, all right, then it seems that there is no more questions. Yeah, thanks again to Woojin and Christoph for the nice talks. And
thank you.
Thank you again. Yeah, I just want to thank you again.
Thank you, everyone.
Yeah, thank you. Okay, take care, everyone. I want to end the meeting. Yeah, thanks.